The first introduction which I would like to give is one of our each and everyone's a very favorite student. That I think all of us must say yes. Because so we give a very warm welcome on behalf of Future Foundation School to Dr. Debasish Banerjee. Let's have a big round of applause. I hope I told class 12 and 11 that this seminar was supposed to be held in the month of April. But due to some unavoidable circumstances, we didn't get the opportunity to conduct that. Later on, that was the lockdown part. Later on, again, we have a discussion with Debashish, and he agreed to come to us. Now, today we have Dr. Debasish Banerjee from the Nucleus Institute, the Shah Institute of Nuclear Physics. Okay, so what we are going to, he is here with us. He will share his expertise and knowledge, so that at least you can gain something and use them in your future careers. I would request now Anjuna ma'am to introduce Debasish Banerjee.
I would also like to say, in continuation of what Debjani ma'am has just said, he was one of our favorite students. And not only in his studies, but in his behavior. And you will always see him with a smile, and he hasn't changed a bit. And we are really very, very proud of him. Yes. And there were quite a few other students also in his batch who were equally good, but yes, we will try and get them to school one day. So here are the details. He passed out class 12 in 2002. That's more than 2 decades ago. And he has been a student of this school, or he had been a student of this school since class 2. He did his BSc from Jadavpur University. Thereafter, he did his MS and PhD integrated from Tata Institute of Fundamental Research in 2011. He did his postdocs at University of Bern, Switzerland, DESY, Berlin, Max, how do you pronounce this? Max Planck Institute, Dresden from 2011 to 2019. Associate Professor at SINP from 2019, mentored 3 MSc students, currently mentoring 2 PhD scholars and 1 postdoc. 37 peer-reviewed papers in internationally renowned journals. I think this should be more than enough, so. So shall I hand over the microphone to Debashish?
Okay, let us welcome Anjuna ma'am with a small token from our school. Debashish.
Thank you so much. I should begin by, of course, thanking Debjani ma'am for the very kind invitation. But also, I have to stress that the impression or the effect that the school has left on me is undeniable. I've studied in this school for more than 10 years, from class 2 to 12, and of course it has been an extremely nice experience, extremely well-rounded experience. I think that's very important. And of course, all the teachers were my favorite, so I cannot single out anyone. All of them have left in their own ways. They have left their impressions on me, so which exists still today and will exist for a long time. So yeah, so it feels extremely nice to be back here, and so I'll try to share with you some of the things that I work on, in my career, and I hope that you will also get excited by this. So of course, the love of science and kind of doing things started when I was in Future Foundation, and I was, and it's not just physics, right? It's science as a whole, and of course, when you say science, it does not mean that you leave out things like literature, right? Those are also very important. When you see, just as in a society, no subject essentially survives alone. So there's always a very good intermixing and intermingling of various disciplines that kind of mingle to give a well-rounded flavor in any subject. And that's also what happens in physics, for example, okay? Right, so I think for the rest of my talk, I will now focus on what I have on the slides here. And please ask questions, right? So the way I will start, the way I've structured this is that I will tell you a bit about what modern physics is, right? What does it mean when you say that I'm doing research in physics, right? You have to appreciate what are the topics one is talking about. So that will roughly be the first half of the talk. And then in the second half of the talk, I'll tell you what can you expect if you choose to have a career in physics, right? Or for that matter, science, chemistry or biology. How does your education look like? And then of course, after having done the education, what are the other opportunities for getting a job and moving ahead in your career, right? So that's how the talk will be structured. And please stop me whenever you have any questions. Always ask me. It's very good to have an interactive session. As you know, one of a Nobel laureate said, it's better to uncover a little than cover a lot. So let's uncover a little, and we uncover it really well. Good. So let's say we focus on theoretical physics, right? So that's what I do. But when you do theoretical physics, the one interesting thing that you get is an overview of the various branches of physics that you have and what are the kind of things that you want to do with it, right? So when you're all familiar with the cube, right? So a cube has how many directions? How many independent directions? 3, right? So there are 3 different directions. And interestingly, if you look at modern physics, so modern physics also has 3 different axes. You can think of them as 3 different axes. And you can look at phenomena along each of these 3 different axes, and they constitute the pillars of physics as we know them. So one of the directions, so let's start with G. So this is this axis. So this G, does this symbol remind anything to you? Exactly. So this is the gravitation constant. That's great that you know, right? This axis, this is something called 1 over c. So c, in case you are you familiar with c? Speed of light. Fantastic. So this is speed of light. Then you know more, all of it. And the third axis that we'll talk about has h. It's Planck's constant. Fantastic. So this means that there are 3 different major directions. One is about gravity, one is about speed of light, which is technically called relativity, and the other, as you said, Planck's constant, has to do with quantum physics, right? So the kind of topics you start learning when you do physics, right? This is, let's say, class 6, class 7, class 8, class 9, these are things like classical mechanics, right? I'm sure you know all of Newton's laws, right? Newton's laws, you have thrown balls at certain angles, where do they fall, acceleration due to gravity, and so on, right? So everything is classical mechanics, right? Now, what happens is, if you ask questions about, this is again something that you know, if you ask questions about like the time period of Earth or any other planet across the sun, right? Or for that matter, any other planet in some faraway galaxy moving across its respective star, you talk about gravity, right? And what was very interesting is that so this is considered one of the very central principles of physics, because this was one of the first times when people realized that a law that, it was empirically deduced, being on Earth, was valid and applicable throughout the entire universe. Right? This was not at all obvious when you think about it. Why is it that the laws that govern us should govern planetary objects, right, which are thousands and millions of times much bigger and massive than us? Right? So this is one of the first such leaps in that direction. Okay, right. So this is when you go in this axis. When you start from your, like your basic physics and you go along this direction, then you come to what is called special relativity, right? So of course, a ball which is moving slowly, or for example, a car on the street, or even a train, one of the super high-speed trains, they still follow the laws of Newton's mechanics, right? Newton's laws. But if it so happens that you have some particles or some object which is traveling very fast, almost comparable to the speed of light, then there are other laws of mechanics that come into play. Sorry? Yeah, exactly. Yeah, yeah. So if the speed is very large, then what happens is that there's a different set of physical laws that come into play. And this was discovered by, or at least formulated by, you know the name of the person? Albert Einstein, exactly. So this is what is called special relativity, right? Now, what happens if you have massive such objects, right? So the special relativity typically applies to ordinary sized objects, right? So for example, us, if we move very fast, you might have heard of things like twin paradox. There's someone who's in a spaceship, goes very far away, while the twin remains here on Earth, and then when this person comes back, he suddenly found that the twin has grown much older than him. Right? This is one of these very interesting conundrums of special relativity. However, if you have massive objects, right, which are moving very fast, right? We have such objects in our universe. Right? These are quasars and neutron stars. Sometimes they can move very fast. Then what is needed is beyond Newtonian gravity or special relativity. It is called general relativity. This is again was discovered by or formulated by Albert Einstein at a time when no one had any comprehension about these abstract physical ideas. And 10 years later, there was some sort of experiment which proved him right. So these two theories on this side are these two theories are like a triumph of pure thought. So all the physics that lies here was kind of reached just by thinking through clearly the foundations, and you have the result. On this side, on the other hand, you have what is called quantum mechanics, right? You know that if particles, on the other hand, are very small, right? Not objects like us or this table or this screen, but rather very small, like atoms and molecules and electrons, then again the standard laws that we know do not apply there. And for that too, you need a special kind of laws, and that is quantum mechanics. Now, unlike the physics here, quantum mechanics was almost exclusively developed by experiment. People in 1900s thought that they had a complete idea of how the world would work. Exactly 1900, so about 120 years back. However, when more and more experiments were done to confirm that view, it quickly turned out that that's not what was happening. So therefore, new laws started, coming into place, and about 100 years back, so in the 1920s, the subject of quantum mechanics, as we know it, started to take shape. Now, what happens if you have these small particles, but moving at very high speeds? Perhaps you've heard of things like CERN, the God particle. You might have heard about this, right? So these are extremely tiny particles. So if you were to take, like any constituent of matter, and you break it down to very, very tiny parts, and I'll show you a cartoon later on how this happens, you will see that these tiny particles, not only are they very small, but they also travel very fast, right? And the physics that is important there is called quantum field theory. So this comprises both the physics of special relativity, where things are moving very fast, as well as quantum mechanics when these objects are very small. Okay, so all these things are on very well-known, as of now, as of 2000, let's say, all these things are pretty well on solid foundational basis. Even though, there's also extensive research here. What we do not know, or at least what lies beyond, are these things, right? So one of the things is non-relativistic quantum gravity. So what happens if you are looking at very small particles, very small scales, but also they're very heavy? Now, have you heard of things called neutron stars? You have, right? So do you know, for example, in neutron stars, even if you take a tiny bit of the matter that comprises of neutron stars, maybe even just a spoonful, it's going to weigh the same as much as Earth. So it's an extremely dense object, right? And at the same time, it's very small. So when you talk about things like that, right, you need things which are called non-relativistic quantum gravity. Things are very heavy, but they're not always moving very fast, right? So this is the area. The other thing which people love to dream about, although there is no concrete thing yet, no concrete theory yet, is called the theory of everything. And I'm sure you've heard of it. Does anyone know any terminology, any name? No, it's something more actually. I'll give you a hint. You must have seen the Big Bang Theory, the series, right? What was Sheldon working on? It was string theory, right? So even if you don't know anything about science, you will know string theory. So this is something that, like other physicists like to make fun of sometimes, of course, in a very joking way. String theory, because it has been researched on quite a lot since the past few decades. There's been a lot of research in it. But of course, there's still no concrete experimental evidence, right, of this. Okay, so this is how, just a broad overview of the physics. And yeah, so essentially I've told you whatever is in this slide just a bit before, that I talked about classical physics, right? And this was to do with mechanics, fluid dynamics, right? You've learned these liquids flowing in some pipes, and then you find the velocities and so on. Thermodynamics, you've learned the different laws of thermodynamics, right? Electrodynamics, gravity. So classical physics is what was in the corner, in the origin of that cube, right? And I also talked a bit about modern physics, which was talked about relativity, quantum mechanics, and then these are all related concepts. Statistical mechanics, for example, is a physics that you need to understand if you have a lot of molecules, right? A lot of identical particles, right? A lot of molecules, a lot of atoms, a lot of us, a lot of people in a room. That's a bit more difficult to tackle, but it goes in the same direction, that you can handle them using statistical laws, right? So here, physics gets influenced by statistics. So the entire knowledge that people have accumulated in the study of mathematics and statistics comes here. And then a more ultra-modern part of physics, I just call it ultra-modern because that's been happening in the last let's say a decade. I mean, some of the ideas existed before, but it's just picking up now. And I heard that you have some courses on some of these stuff as well. So this is a bunch of stuff. So what I heard you have already been doing is about artificial intelligence. At least you've been exposed to it, right? So artificial intelligence is very closely linked to this idea called machine learning. So machine learning comprises of the fact that instead of a human brain, so human brain is kind of a biological computer, right? Because it develops, it's a biochemical computer, because all these neurons and all this, they function with biochemical reactions. That's how you have stimuli, we react, and so on and so forth. Now, if you have a machine, if you have a computer, can you train the computer to behave to behave like a human, right? So that is one of the basic questions. The full culmination of this would result in artificial intelligence. That if you can teach a computer not only just to respond, but have creativity, have emotions, right? Then it would have, you would get what is called artificial intelligence, right? And this, of course, has a lot of societal impact, right? So here is an example of a branch of physics which is not just purely intellectual based, right, or experimental based, because whatever artificial intelligence comes out, or whatever form of AI comes out, it's something as a society one needs to be extremely careful about, right? So that's machine learning, on the other hand, is a more primitive aspect of artificial intelligence. You have a well-defined task, and you give the task for the machine to solve, right? You might have heard of ChatGPT. Have you been? Yes. So you can ask ChatGPT, you want to go for a holiday in Agra, for example. You can ask ChatGPT to prepare an itinerary for you, right? ChatGPT will do that. That's, of course, as you said, it's been exposed to various other things on the internet, and from looking at other things, it forms it recognizes your basic query and gives you a tailor-made answer, right? But of course, so this is an example of machine learning and to some extent artificial intelligence. But artificial intelligence is far more complex, right? The other thing I want to emphasize is this thing called second quantum revolution. So the first quantum revolution happened 100 years back, right? Because people learned to think differently. So the laws of physics as applied to tiny particles are different from the laws of physics that govern macroscopic particles. Second quantum revolution is a more technological revolution. There is no change in terms of understanding these particles. These laws remain the same. What has changed, however, or what is changing at this moment, as you're all listening to it, is our capacity to harness these quantum technologies. You're all familiar with computers, right? So that's a desktop, that's a laptop, and you have desktops, right? Now the point is, these are all classical computers in the sense that they work with superconductors, right? These are all these classical bits, zeros and ones you've learned in your computer science classes. But what's important is that these second quantum revolution works completely differently. It has different architectures, right? I'll briefly mention it in a point, at some point. So these are the three different topics, right? Broadly speaking. Again, let me just quickly tell you a bit like what happens in these branches. And once again, you should, if you have any questions, please interrupt me, right? Raise your hand or something and ask. So when we talk about these particle physics, right? Particle physics is a physics which has to do with small particles moving very fast, right? And the idea here is that you have a mathematical theory which explains the entire universe, right? Like why is it that the universe comprises of so much matter? Why is it that the universe has a certain part of radiation, the photons coming, right? So these are all questions that one wants to answer, and one wants to answer in a very bottom, like from the bottom up approach. You postulate that there are certain particles which are interacting in some way, and then from that you can explain essentially everything. The idea is similar to what you do in Newtonian mechanics, right? You have a car, for example, or a train that's moving, and just by solving some equations, you can predict what's going to happen in some point in time, and so on. Exactly, the idea is same here. The philosophy is same here. You have a bunch of laws, and these bunch of physical laws should explain how these particles are going to interact with each other. And as a result, it's going to tell us how are we made of? Like why do we have a mass? Questions like that, right? So this is an example that you see of a state-of-the-art experiment that requires, so these experiments in particle physics, these are called collider experiments. So how do you do it? So what is the philosophy there? The philosophy there is the following, that suppose I want to know what is contained inside this, of course don't try this experiment by yourself, right? This is a statutory warning. So if you want to find out what is there inside this pointer, right? What does one do? Suppose you don't know how to open it, right? So there's a physicist called, a lot of physicists, they said that, the simplest thing is that you break it. You take two pointers, you shoot these pointers at each other, and then you shoot them with such high speed and such high momentum that the momentum breaks apart this pointer. And then once it breaks apart, you suddenly see that, inside there are batteries. Inside there's a screen. You start to appreciate what is inside this composite object simply by breaking it up. It's a very primitive tendency, right? But you can go ahead and do it. This is exactly what physicists did with particles. If I want to know what is contained within a proton, how do I do it? Just break the proton, smash protons into each other with such high momentum that they break apart, and then see what is contained inside it. This is exactly what has been doing, what is happening in CERN, for example. People prepare these beams of not only just protons, but heavier nuclei, and they just smash them onto each other with extremely high speeds. And because this thing needs to be so accurate, and this thing needs to be so precise, it needs a multi-country collaboration. It's an international collaboration of physicists across the world. So these experiments have as many as 2,000 participating scientists, right? And it's a very interesting thing, because you have your colleagues spread across the entire world, and it's a fun team activity, for example. Okay. Then the other branch of physics, which is very technologically important, is called condensed matter physics. So condensed matter physics is essentially the physics of materials and phases, right? So you know that there are, basically that there are three phases of matter, right? Very, very generally speaking. You have solids, you have liquids, you have gases, right? Now, what if you were to design special solids or special liquids with some special properties, right? Has any one of you heard about, so typically think about the fact, liquids, right? Liquids, the usual liquids have viscosity. You have some notion of viscosity. So if I give you a glass of water and a glass of honey, which is more viscous? Honey, right? Because you move, for example, you take something, you drop it in honey, and that object will immediately stop, right? It will stop much faster than it stops in water, for example. Now, what if I tell you, so viscosity is friction, right? It stops, it kind of removes this initial momentum. What if I tell you that you have certain liquids which does not stop any moment, which does not stop anything? So you have certain liquids called liquid helium. And in this liquid helium, it has zero resistance. So if you move something in liquid helium, it's going to move on forever. It's never going to stop. And when you have such exotic objects, exotic materials, I say it exotic because it's not something we are familiar on our everyday life, then you can think of having new technologies, right? So one of the very cool technologies that people came up with is this idea of magnetic levitating trains. You must have seen the trains, you must have heard about these trains in Japan and China now. So these trains go extremely fast. How can they do that? Normally what happens, a train has wheels, metal wheels, it's running on some steel rails, right? And of course, that's much less friction than moving on the ground, but still there is friction, right? The friction is not zero. So the idea is that if you can make new kinds of materials, right, which do not have any friction, then essentially you can engineer these surfaces in such a way that the surfaces can glide on top of each other without friction. And therefore, you need less energy even to make the trains move because the energy is no longer being wasted as friction, right? So these kind of things have changed. Yeah, there's a question.
Sir, if there is no reduce the friction so that the trains move faster,
Yeah.
then it will become equally difficult for the trains to stop, right?
Yeah, good. So what happens is that, exactly, very good point. So this is exactly the kind of situation where you need to have a knob on what you are doing on the material. So you see, if I say that I have a material and I cannot do anything to its properties, then I am not doing any better. But one of the things in condensed matter physics is to look at different kinds of phases and how you can change these properties by applying, for example, pressure or temperature. So this is the study of the physics of of how these properties change. So for example, it can very well happen that these phases which have no resistance, right, no friction, this phase happens below a certain temperature. As soon as you raise the temperature, the property changes. So these things can be used, for example, as you said, to stop the train. So the physics of such things is called condensed matter. This was just a very crude example that I gave you, but of course a lot of condensed matter physics, material science has given rise to our cell phones. The fact that you must have seen, I mean, to me this is already a fantastic thing, right? You have liquid crystal displays, and nowadays you can fold liquid crystal displays without leaving a single smear in it. How is this possible? Normally you take materials, paper, you fold it, it leaves a crease behind when you unfold it, right? And now we are talking about these electronic displays, which I'm pretty sure if I fold this, it's going to leave a crease. But nowadays you have some special mobiles, right? Special screens which are crease resistant. So you can do a lot of innovation, a lot of technological development if you properly understand how to generate, how to manufacture new kinds of materials. So this branch of physics, the motivation is different. It's not that I want to understand the nature as much, but using the properties that are present in nature, how can I create new objects, new devices that is, of course, will be helpful to our civilization or society as a whole, right? So this is more technological aspect. In fact, this is exactly what I was trying to tell you. Material science, you have LED screens, and in fact, not only just technology, right? So for example, it turns out that there is a material called graphene. Have you heard of this thing, graphene? So graphenes are sheets of carbon. They're extremely thin, but they're extremely strong. They're among the most strongest thing that we know. So you can in principle, graphene is finding more and more technological uses in medicine, for example. In biotechnology, if you want to channel something, if you want to give some sort of a medication inside a very sensitive organ, You can create a tube which is made of graphene, some sort of a nanotube, and you can insert the nanotube through some orifice, and then you can put whatever medication you have directly to the organ. And the shape of this graphene is an extremely is a flexible object. You can shape it in any way you want. You can make this into nice tubes, you can make this into buckyballs or any other shape. And this allows you to target exactly the kind of organ which, for example, has a problem. So you see, with this kind of technological development, you're also helping medicine, right? Saving people's lives. So yeah, so that's what it is. The other branch, which is also extremely exciting, and it goes in the direction of particle physics, but does not talk about tiny particles, but on the other hand talks about big scale structures, right? Now all of us, when we grow up, right, we look at stars, we look at the sun, we look at moon, we look at clouds, we get mesmerized. We look at, if you have been lucky, if you are away from the city and you're in a deep remote area, you can look at the stars, you might see star clusters, right? Galaxies, for example. Constellations. So these are huge macroscopic objects, right? Beyond what we can imagine. Of course, we've seen enough sci-fi movies, read enough sci-fi books to they act as an impetus to our imagination. But this look at this picture. This is an area of the universe which is huge, and this has so many galaxies inside this. So you see, there are all these bright spots. And these bright spots, each of them are galaxies, with each galaxy having, I don't know, about 100,000 stars, 100,000 solar systems. So when you look at the shape of the universe, you realize how tiny we are, right? How really like a speck of dust we all are. And this raises many interesting questions, right? So what if there are other civilizations existing beyond the one that we know? Why have we not found sources of that civilization? So that's a more, that's not the question that astrophysics tries to answer. There is other, sorry?
Is that Fermi paradox?
What is the Fermi paradox?
Something related to particularly to this.
Yeah, so yes, so perhaps there's a related to this. I'm not sure of the exact term, but there is something called the weak anthropic principles, but I'm not going to go into that. This is perhaps what you're trying to imply, anthropic principle. But anthropic, anyway, so I can relate to the anthropic principle later. It's a more of a philosophical principle than a scientific result. But what is interesting is that you have, because of all the developments in science, it is possible now to understand properties of this universe, right? Actually detect the properties of this universe, even from this Earth. Now that's a very challenging statement, right? Imagine, you are here on the Earth, you are here on one of these tiny dots, right? And yet, you are able to make measurements which make millions of stars visible to you. And for us to sit at this seminar and wonder at these pictures. So there was a telescope, NASA, so you must have heard of NASA, North American Space Agency. So they launched a telescope called the James Webb Telescope, a space telescope. And I'm pretty sure you've come across some of the fascinating pictures that the James Webb Telescope has sent, like the rings of the Saturn and the huge, huge gas clouds of Jupiter and so on. Those were near things, right, in our solar system. They are a neighbor, so to say. But then you have things far away, like this galactic nebula, which comprises of such huge number of stars. And these are things people are trying to explore. There's, of course, a branch of space science which tries to look for Earth-like planets in nearby solar systems, right? So because you have an advanced telescopes, you have advanced measurement systems, you can define criteria that how do I see a planet, and how do I understand that there is a atmosphere on the planet? How do I search for humans or any sort of intelligent civilization, right? So these are very interesting questions that take you beyond just physics. On one side you have physics, but on the other side you have various kinds of biochemical reactions that give you certain things in the atmosphere, right? Then you have to appreciate or imagine what kind of civilizations can emit what kind of signals. If we are a more advanced civilization, like the one which kind of evolves a lot of carbon dioxide, for example, you all know about global warming, right? We are just spewing tons and tons of carbon dioxide in the atmosphere. Because of this carbon dioxide in the atmosphere, the sun's light, when it reaches atmosphere, certain wavelengths are absorbed. I mean, I'm sure you know this model of atoms, right? There are all these energy levels, and depending upon where the electrons are, the sun's light comes, certain levels are excited. This means that you can see certain spectra, and this is exactly how you identify what kind of gases exist in the atmosphere of a planet. So it's much beyond physics. You have to anticipate what kind of civilization can exist on the planet. Is it a carbon-based civilization like we are, or is it a different based civilization? It can happen. So here is a space for doing even very creative ideas, exploring your creative ideas. Then there has been even more basic but like very interesting things about gravitational waves. This has to do with Einstein's general relativity, what I told you. Have you heard of things called neutron stars? You just said you had. But if you've heard of neutron stars, you must have heard about black holes. Right? Black holes spur the imagination because black holes are supposed to be extremely massive objects from which nothing can escape the gravitational pull. Right? The gravitational pull of black hole is supposed to be so strong that light does not escape. That's why it's called black hole. Right? So do we know that black holes really exist, or is it a figment of imagination? So this question, of course, people can now detect, and we know that black holes exist. And furthermore, we know that these black holes are scattered in our universe in various points, and they are rotating because you see, if black holes, you know that, from classical gravitation, that if you have a body which is very massive, right, then the lighter bodies start rotating around it. Exactly what happens in the sun. The sun is much more massive than these planets, and therefore planets rotate around it. If you have big black holes will also make other objects rotate around it. Sometimes they will go in and merge with each other. So this is not really a black hole, but this is like a neutron star. But these days, with advanced telescopes, you can actually detect the radiations that come out of it. So because these things are, this is far advanced for me to explain, but let me just try a very naive example, right? So imagine you have a fabric. Now you have to think of it. Imagine you have a fabric, right? And I put a heavy ball in the fabric. Then of course you have planets that go around it, right? But the entire shape of the fabric is more or less governed or more or less decided by this heavy ball. Because the other balls are very, very light. It's not going to change much in the fabric. But what if I put two heavy balls? The two heavy balls will start rotating around each other, right? And at some point they will collapse. You can try this experiment. Like later on, you can take a big sheet of a bed sheet and take two heavy balls and put them on two different ends. You will see that they'll start rotating, and at some point they'll come and collapse. This is very similar to what happens if you put two big black holes next to each other or at some distance apart. They will start rotating against each other, around each other, and they'll come and collapse. And when they collapse, the fabric will start moving, right? And you can detect these vibrations in the fabric. In this case, in your case, the bed sheet. And you will detect these very regular oscillatory patterns, and that tells you something about the universe. Right? And again, imagine how great is it that you have thought about the existence of black holes solely on Earth, right? Based on phenomena which you see on Earth. And then you can predict something that is happening millions and millions of kilometers away, even light years away. Right? So this is the power of our capacity to imagine, our capacity to understand, right? So can an artificial intelligence do this? Can you ask an artificial computer, like a machine AI, to come up with such new physical theories? These are very challenging and interesting questions here. Okay, so yeah. So I think I'm going to So this is again quantum computers. This is the last bit I have about physics before I move to. Exactly. So quantum computers, as I said, they operate on hardware which is basically very different from the hardware we use in these desktops, right? So the desktops, you've heard of chips, right? These chips are the ones that populate our phone, right? However, in quantum computers, they do different things. They are called qubits. And you must have heard about classical bits, right, which takes only 0 and 1. All I'll tell you is that qubits, because of certain very special properties of quantum mechanics, can store much more information. Not only just 0 and 1, but it can store all values in between 0 and 1. Yeah, so I have to write down a mathematical equation, which I'll not do at the moment. Even irrational numbers. It can store everything. So this also means that one has to rethink our classical algorithms, right? The way you add two numbers, right? The way you do addition, subtraction, multiplication, division, right? All these are usual classical algorithms. If you want to divide 756 by 7, for example, there's a certain rule, right? You take 7, 757, and then you see how much of 7 goes into each, right? So these are classical deterministic algorithms. We are never taught that way, but these are just algorithms, just another way of finding out a procedure. But quantum algorithms are very different. They essentially work on the premise of probabilities, right? So one needs to get acquainted how quantum algorithms perform. And in fact, just as out of curiosity, if you are interested in finding this out, you can even type IBM Q. Just these 4 words, IBM Q, type it in Google and see what comes out. There are publicly available quantum computers. You can create an account just as you do in Google, Gmail, but actually use these quantum computers to play around. So that's something fun. IBM Q. IBM is the name of a company that was making computers quite a while back. Q stands for quantum. So they're making quantum computers. So IBM Q. I've already talked a lot about machine learning and artificial intelligence, and this is just some cartoons that tell you what is happening is that you have some sort of, from biology, we know that we have these neurons, right? These neurons collect the stimuli, and whenever the stimuli, in terms of some chemical reactions, right? Whenever the stimuli cross a threshold, a certain message is sent, a certain kick is sent, and you react accordingly, right? And you have these various neurons spread all over your sensory system, right? And then they collect the stimuli, and then they send the information to your brain or the spinal cord, and accordingly you react, right, in a certain way. So you try to build machines also similarly. You have lots of these computerized neurons, right? These are neurons which are the artificial neurons, and these artificial neurons take in stimuli, which means you have some function, you send a value of the function, and depending upon if this value crosses a certain threshold, a certain action is recommended, certain value of the function happens, right? So yeah, so you see there are various different architectures of neurons people explore. One is simple neural network, deep learning neutral neural network, and so on, right? So there are many such things here. Okay, good. So this was about an overview, and let me come to the second and the part where I expect you to ask me more questions. Yeah. Yeah, so I will have the tea as soon as you ask some questions. So now you have an onus on you to ask me questions. Thank you. Right. So the next part, what we should talk about a bit, is that if you want to study these kinds of aspects, what are the skills? What are the kind of skills should you come prepared with, right? So, and believe it or not, all these skills are things that you learn in the school education. These skills I have learned here in this school. So all of you have it, I'm pretty sure. I'm just summarizing them, right? So you have a curiosity about things work, right? So you are curious about trying to understand, like, how is this mobile phone working? It doesn't mean that you need to know all the details, right? You can just look up. You should have the capability of looking up certain things for yourself, or ask your teachers. They're extremely wonderful, and they've always, they will never say no to any questions. They've never said no to me for any questions. So have a curiosity, right? And try to satisfy your curiosity to the maximum extent possible. Then you have to be skilled in analytical and critical thinking, right? So in many cases, we have facts, and we accept facts as they come to us without thinking too much, right? Which is good up to a certain point, but you need to make sure you have at least an empirical way of understanding the fact before you accept it. And this is not just true in physics, this is true for everything else. Someone gives you a fact, any fact, think about it for a while before you accept it. So this is your skill, and you have to understand and comprehend the fact for yourself in your own way. It doesn't have to be the universal way, but some way, somehow you have to understand this fact. And then, of course, you have mathematical and logical manipulations. That's exactly what many years of maths teach you, right? Programming skills, again. So this is another important thing. If you know how to logic, if you understand the logic well enough, if you can reason out how to solve a problem, right? Then you will automatically be very good in computer science. Because sometimes you're asked to write programs to solve certain problems, right? You have to first think, what is the most optimal way to solve this problem? And that thinking requires this number 2. You have to think about it. What is an easy way to do it? It can be a very difficult way to do it still, but there's a logic to it. That logic is very important. Once you know the logic, everything else follows automatically. It's the same in mathematics, same in computer science, same in many branches of research. Then, some people, not me by the way, if you're good in making and building things, right? So if you can create things, right? It can be art, it can be crafts, it can be an imagination, it can be a painting. It can also be real tools. You can take tiny tools and you can actually build up some sort of structure or something. Then these experimental aspects of some of these detectors and physics that I talked about could be a good field for you. If you're naturally inclined to doing things with hands, this is a very, very valuable asset. This is a very, very valuable asset that is very integral to the development of all the basic sciences. Because you need to be able to build things, right? It doesn't matter. That doesn't have to be very good. You have to build things. That's a very, very crucial step. Right? Even if things break, they have to be built before they can break. So you have to build. That's the thing, right? And then, of course, this is quite important. You have to. Sometimes there are, you see, as I said in number, is that you get handed down facts, especially in this information age where information is literally exploding. You are handed down facts from all areas, right? And it's impossible to check and verify every fact. This is true. You'll realize there's too many information. You don't have time to process the information. So sometimes these information that they come from preconceived notions that may or may not hold. And there is no easy algorithm for me to tell you that this will work and this will not work. So this is something one has to inculcate, right? This is something, a training that has to happen within yourself over a long period. And so you have to get rid of these preconceived notions which do not work and other preconceived notions which work. Exactly, right? So if you're exposed, if you're exposed a picture, you should be. One should be aware that there are deepfakes around, and before I accept what the information in the picture, I should be careful that I should allow a possibility of doubt in there, right? So these are things that you should have in your mind, right? It doesn't matter whether you say it or not, express it or not, but these are things that should be there when you're processing this information. Good. Any questions? Any questions in the last slide? Yeah.
We talked about liquid helium.
Yeah.
Like vacuum.
No, liquid helium is not vacuum. So vacuum essentially has nothing, right? So it's very difficult to make a vacuum out because then you have to pump out all the air and so on. Liquid helium is a new form of matter. So you know helium gas, right? So if you take helium gas and you cool it down, as happens for most gases, it's going to liquefy. But liquid helium, in contrast to liquid water, has essentially a vanishing viscosity. Just as I was telling you, right? Different substances have different phases. So honey, for example, honey again is a liquid, but it's a very viscous liquid. So liquid helium is a special type of liquid which has very, very low viscosity. It's not zero density, it is a finite density. So it's not vacuum, but it's very low viscosity. Yeah.
So liquid helium has lesser friction than air.
Yes, for sure. Because, yeah.
So that means if we are put in a room which has liquid helium, no air, so running in that will be easier than running in.
Yes. Just imagine it's not you, but because to create a human-sized liquid helium chamber is quite difficult. But imagine a particle, right? This is what I said. So normally you can take a ball, right? And you take up some sort of a ball and you throw it from there, right? The ball will come and fall here. It falls here because, of course, there is some, I mean, ideally it would fall somewhere, but of course, if you take into account the fact that there's resistance, some part of the heat is dissipated, right? Some part of the initial kinetic energy is dissipated. If it's a liquid helium, it's not, there will be virtually zero dissipation. It's just going to move far away and only be attracted by gravity. That's all.
So it is kind of an ideal situation.
It's a very ideal fluid, right? Okay, so now the question is, having known all these things, if you've seen what kind of skills you need, at least from my perspective, but what does a career in physics look like? The first thing is that it's hard. I'm not going to lie to you. It is hard. It's not very easy. You should be motivated, and you should really be passionate about your aim, right? Because this is really, I mean, if you're interested in doing something, it's really, you're in it for a long haul. It's not something that you can start and finish in 2-3 years. It's more than that. The reason why this is important and the reason why it takes long is that you want to do something which is at the forefront of our accumulated knowledge. Our accumulated knowledge is growing day by day, right? So you have to find, and this is a very viscous medium. Imagine the knowledge, imagine a liquid, imagine a room filled with knowledge, right? Knowledge is a very viscous medium because you have to move. As you move, you cannot just move. You have to imbibe that knowledge, infuse the knowledge into yourself, process it, and then move forward. This process takes time, and therefore I'm creating an analogy with viscosity. It is a viscous medium, right? So because the knowledge, the accumulation of knowledge is large, you need to find your optimal way to it to go to the end, where you can make contributions which are really at the forefront of the knowledge. So this is hard, and this is, and therefore the motivation, right? You need to be motivated. There's no second thoughts about this. Typically what happens is that you have to do bachelor's, master's, PhD. This has been the time when, like when I was doing my studies. But these days, you can do different things. There is this national education policy coming up, which essentially means that the master's part is going to disappear very soon. So this means that you're going to have a 4 years, typically a 5-year bachelor-master thing. But it's just one degree. In very soon, in a few years, the institutes will mostly have, will give you a 5-year bachelor-master degree. And what is very good nowadays is that they insist that you have 4 years of formal education, like usual classroom lectures and laboratories that you have, but 1 year you really spend going to a different institute and doing research there, like an internship. This is very good and very timely. This has been the case in Europe and North America for a long time, but we didn't have it before, and it's very good. This sort of a thing is very welcome. Because most of the things that you actually do are related to what you learn as your intern, right? There are different types of education. One type of education is necessary in what you get in your lectures or your classes. Very important. Laboratory is very important. But the other type of lectures is when you go out and interact with people who are working in the field, and you learn how to do it, learning by doing, right? I'm sure you do it more these days, but at least this is happening in higher education more and more frequently. And so also the other point is that you have various combined degrees possible. So it's not just, if you, for example, what would you do? Let's say you are interested in physics, for example, but you're also interested in literature, right? It can happen, right? So previously in our times, it was not possible for you to take, if you're studying, for example, a physics degree, it was very difficult for you to take an extra course in history or in literature, for example. But these days, at least in the way that the education is progressing, it's supposed to be much easier. You can get courses for completing credits in literature or history or philosophy, and they get transferred to your main course, right? And that's good. Because imagine, you can also do your studies in science, and you can also be a writer, you can also be an author, you can also be you can also influence society in that way in doing science education. That's also a very, very important career option. So you can also do this after having done your bachelor's and master's. You can look for jobs in the industry. The situation in the industry is, of course, much better these days because there are many initiatives, many startups, many companies which have their offices in India, and there's a lot of innovation-based development going on, right? Because at some point in our development, a lot of it was just IT. You were doing IT, you were doing consultancy a lot. So this still dominates the world, that still dominates the education sector a lot. But you still have options for doing, working with various startups and various companies which are producing products which are based on innovation. For example, there was some sort of a product, I mean, you get to hear about these in the media all the time. There was a machine that they were being built and at least trying out, which sucks water, or rather, from humid air and creates potable drinking water. For a place like, for a climate like India, this is quite good because our air is is very humid. So if you can process clean drinking water from air, that's already a very good thing. So these are kind of nice ideas you can act on them. And many startups are actually funding these kind of developments and processes, right? Yeah. So this is just a cautionary statement, unlikely to compete with students who have studied engineering. This just depends on the kind of jobs. I mean, typically, the students when you do engineering, there's a certain tailor-made process in most of the institutes where they try to get you jobs. But when you do science or when you want to do research, it's not just about the standard jobs, run-of-the-mill jobs that you're looking for. You're looking for jobs that challenge your intellectual and creative capabilities, right? So that is something where you can compete if you really have a passion for doing it, right? If you have a passion for trying to change things as they are for the better, right? You always will have a niche when you study these kind of topics. You can decide to do a PhD, and typically what happens after your PhD, this is underquote, your net worth increases because the entire time you spend doing a PhD, which is typically between 3 and 5 years, depending on where you do it, it gives you an intensive training on how to solve an original problem. So when you write a PhD thesis, you will have written papers or at least solved problems that have not been solved before. This is what is typical in a PhD. And once you do that, it really gives you the required confidence to move forward and start implementing the changes that are in your mind. Because this is a very crucial thing. Remember that we all have many ideas in our minds, but it's not always possible to act on them, and even less likely to finish them up as a finished product. This requires a lot of activity, not only from our part, but also in terms of bureaucracy, in terms of getting things done. Because getting things done does not always depend on you. You might require some sort of experimental setup for which you need to go and talk to some other person. So you have to navigate these things and successfully conclude this. So that does not only depend on you. So that's exactly what I'm saying. Once you've done this, once you've gone through this exercise, you have what it takes in you to take future projects on your own. So you have a complete independence of thought and actions. Yeah, so this is what this is, and now you can advertise your work. And typically, once you've completed your PhD, as I've seen among many of my colleagues as well, you acquire an extra level of competence which many companies are very excited to have. I will mention this later as well. So then, so after this, you typically have some postdoctoral positions. How long you do them, it's completely up to you. And then you can look for positions as junior professors or faculty. So that's more like a thing. Another interesting thing is that when you're doing research, you typically get to go to various conferences on your chosen topic, whatever you're working on. And that's a very exciting feeling because people from all around the world or around the country are coming there and they're discussing about the same ideas or similar ideas that you have had. And you have the chance of actually seeing how much you have advanced yourself. You can get into collaborations, you can work together. Because for me, working together was always fun, is always fun. So typically when more people work together, then there's a chance that progress happens faster. Right? So these are kind of things that you can expect. So what are the typical places you can expect to study, hope to study? So as I said, there's some sort of a new educational policy is supposed to come in. It's already being implemented, and it is trying to change very much the entire education system. I'm sure that the education at the school level will also get changed, will also get reorganized a tiny bit. But for me, I will just stick to what the higher education does. And as I said, one of the key things in this new education policy is that it will emphasize interdisciplinarity much more than previously. So previously, if you're studying, like field in science or commerce or arts, they were pretty much islands that never talk to each other. So the idea is that there will be new big institutes will be created, which will be multidisciplinary host institutes, and they will allow the students to have flexibility of choosing a variety of subjects from different disciplines. And this will create some sort of a synergy that exists in other countries, but not so much in India. And hopefully that will create a more cohesive society. Not only just society, but knowledge and knowledge transfer between different islands of thought. And that's very important. Once you have knowledge transfer, you will see that things get done much faster. There might have been one branch of knowledge existing in one direction, and once you have that knowledge in a different field, you may process things much faster. So there are various universities. You have Jadavpur University from where I studied. You have University of Calcutta. But on the more modern side, you have institutes like Indian Association for the Cultivation of Sciences. So that have programs already starting from bachelor's. It's very close by in Jadavpur. Some of you may know it. Then there is this central institute. So all these are central, not JU or CU, but IAC is a central institute. These are also central institutes. Indian Association, so Science Education and Research. Indian Institute of Science Education and Research. This is a typo. ISERs, right? So ISERs are created very much in the same model as IITs. I'm sure you know IITs, excepting that the focus of ISERs is more on fundamental research and fundamental research, not only just science. They aim to do science as well as arts, right? So science and humanities. So they're going to talk about more on a broad class of topics. In addition, you have more specialized research institutes where you can join after you finish your master's, for example. So there are institutes like from where I work at, the Shah Institute. You have S.N. Bose Center for Basic Sciences. You have Bose Institute, Indian Statistical Institute, VECC, Variable Energy Cyclotron Center. And so one thing I should stress, I have not stressed at all, is that Bengal has witnessed, so since, ever since modern science came along, right, Bengal has really witnessed some of the very crucial scientists who have been here and who have made progress. The only Nobel Prize winning work from India, do you know who is this? Who won the only Nobel Prize in physics from India? C.V. Raman. Do you know where his Nobel Prize winning work was done? In the University of Calcutta. Right? So there was a C.V. Raman, there was S.N. Bose, who founded, Bose Statistics, Bose Gas. There was Meghnad Shah. So all of them, so one of the first computers in India was installed in Jadavpur University. So there was a lot of fundamental development happened in Bengal per se. So, and if you go to physics, right, from where I'm from, there is a very, you will find that there's a huge number of Bengalis studying physics, theoretical physics. It's a very huge anomaly on the national scenario. Most of the people that you see are just Bengalis, or at least having educated in Bengal. So, yeah, this is just a fun fact. And also, by the way, Indian Statistical Institute, which was founded by P.C. Mahalanobis, it's one of the very first institutes of which formalized data taking measures. Because see, all these ideas of sensors collecting data, storing data, this is a much more recent science. Statistics is a much more recent science, about 100 years old, less than 100 years old. And ISI has played a very central role, at least Mahalanobis and his colleagues have played a central role in formalizing many of these techniques on how to reliably collect data. Right? Because you see, in countries like India, challenges were there. Like you had to vaccinate people against polio, smallpox, all these things. Right? To implement such effective schemes, you needed to have a data collecting centers, right? You collect the data, and so therefore that's how all this was done. On the scale of India, okay, how much time do I have? Should I? 5? 10, 15 minutes. Okay, good. Then it's a comfortable thing. Good. So of course, I mean, not only just Calcutta, you should look, I mean, whenever you study science, right, or you want to do research, one thing is that you have to think on a much larger scale, right? You have to think on the scale of, I mean, these are all just places to study, right? You have to expand your horizons. So there are various places in India where you can study. So the first thing is that I should emphasize is this role of the ISERs, right? So ISERs were made in the same form, in the same avatar as IITs, but with a focus on more fundamental education than technical education. So IITs are extremely good for engineering sciences. ISERs are kind of aimed towards more basic research. And you have ISERs in a host of places. You have Pune, Kolkata, Mohali, Bhopal, Trivandrum, Tirupati, Behrampur. So I'm not sure if more are coming up, but at least these are. I think there's also one in no, not in Mandi. But anyway, so there are already, so each of them have really big campuses with a vibrant student life and also a vibrant faculty. Because another interesting thing you have to remember while you're choosing this is that most of the, I mean, when ISERs were established, ISERs are a much more recent institutes, right? And ISERs have actually recruited faculties who have been trained not only in India but also abroad. So most of the faculties there are very young and very vibrant, and they can give you much up-to-date information than of the many older, more eminent institutes like Calcutta University or Jadavpur University. It's nothing, it's just how things are constituted, and when taking decisions, you should keep this in mind. Then you have another similar institute which is called NISER. They're only placed differently because they're funded by a different institute, Department of Atomic Energy. ISERs are funded by, I think, MHRD. So this is NISER. This is exactly the same role as ISERs. You can join there as in your bachelor's courses, and you can do all the way up to a PhD, but not necessarily. You can always change after your master's to apply abroad and so on. I will come to that later on. So then you have this Indian Institute of Technologies. So IITs, in your undergrad, they typically serve as engineering colleges. So if you want to do engineering, if you want to build things, if you want to learn how to build things, you should definitely try for the IITs. IITs provide a very quality education which is internationally recognized, the brand IIT, and you get to hear that there are lots of innovations happening in IIT, like from IIT researchers very frequently. And there are IITs, of course, everywhere, but these are the oldest ones are in IIT Kharagpur, Kanpur, IIT Madras, and Bombay, Delhi. So these are all the old IITs. And then there are many new IITs. IIT Dhanbad is actually Indian Institute of Mines, ISM. They've just changed the names. In Varanasi, there was the Banaras Hindu University, which is converted to IIT Varanasi, then IIT Guwahati, Roorkee, Patna, Mandi, and so on. There are a lot of IITs around. But the old ones are, the very famous ones are the ones over here. Then there are other institutes which are very much like Shah Institute, but they do specialized research, right? So among the two most famous of them is Tata Institute of Fundamental Research, TIFR, which is in Mumbai, and the Indian Institute of Science. So they are both, very old institutes. And IISc was established by C.V. Raman when he moved to Bangalore. TIFR was established by, did any of you see a Netflix series that came up of Homi Bhabha? So TIFR was established by Homi Bhabha, as was BRC, Bhabha Atomic Research Center. So TIFR is a general science institute. It does research in all branches of science, including chemistry, biology. So if you're interested in that, you should also check out TIFR. I mean, most of these institutes also work for chemistry and biology. I'm just not, I'm just saying this for physics, but this is true for other aspects as well. So TIFR and IISc specialize in physics, chemistry, biology, and so on. The other institutes are more physics-based. So you have Institute of Mathematical Sciences, IMSC, which is excellent for physics, mathematics, computer science, theoretical computer science. Excellent. You also have Raman Research Institute, also established by C.V. Raman. Institute of Physics in Bhubaneswar. You have Harish Chandra Research Institute. Harish Chandra, the name may not be familiar to you, but he was a very famous Indian mathematician. And then you have Bhabha Atomic Research Center. So BRC is a more nuclear technology based. That the primary focus is on nuclear and anything related to nuclear. This doesn't always mean things like bombs, right? It also means things like how can you use nuclear technologies for medical purposes. A lot of, for example, a lot of treatment of cancer, right? It really needs you to bombard patients with appropriate beta rays or gamma rays. So all these things need a lot of research. So material science needs a lot of research in nuclear. So the nuclear technologies are very important. We are facing a climate, we are facing an energy crisis, you must know that. We cannot depend upon non-renewable sources anymore, coal, because they're extremely polluting, right? So, and then of course there is this nuclear power. Nuclear power has been controversial for a lot of ways, especially after Fukushima accident happened. But there are also alternatives to nuclear, nuclear powers which are safer. So for example, you know of nuclear reactors, right? It still does fission, but the typical problem with nuclear power is that the end products are still very radioactive. We don't know where to deposit the end products of nuclear reactors. That's the big concern. However, in certain thorium-based reactors, the end products are not radioactive, or at least their half-life is very short. So their radioactivity goes away very fast. And in fact, India was a pioneer on thorium-based research for a while, but yeah, things got derailed and so on. But that is an alternative, a promising area where you can do thorium-based nuclear reactors and they can generate power for you, right? And then you have, other universities as well. So if you want to study abroad, right? That's also a very common option that is becoming increasingly common to this generation of students. And traditionally, the popular destinations for studying abroad were to go to the United States, Canada, and United Kingdom, right? Partially because the main reason was that the universities there were offering courses in English, right? So, and of course, they had very good universities. In mainstream physics, it's common to do a PhD there. It's very natural that, if you do a bachelor's or a master's from an ISER, you go to PhD in one of these institutes. That's fine. But these days, in the last, let's say, 5-7 years, continental Europe has also become a very popular destination for doing your higher education. So Germany, in principle, is particularly good for very good universities. So Germany has an extremely good education system. Many universities have started to offer their courses in English, undergrad as well as your master's in English. And in addition, you have Scandinavian countries, Norway, Sweden, Denmark as well. You have France, Netherlands, Austria, Italy, Spain. So these countries are less so than the ones mentioned above, but they're also opening up a lot of opportunities to giving courses in English. And then there are other countries of course, you have Taiwan, you have China, Japan, Singapore, Australia. These are also very popular destinations for you to look for universities to study. This list is not complete, but I'm sure it's quite large for you to look a place in. So, having done physics, so let's say you choose to do a career in physics. If you have in chemistry and in biology, you have more options, but I'll restrict myself to physics here. So what could you do, right? what are the possible careers you can have? So of course you can work as an academician, a professor, research scientist of either a PSU or private university, right? So also another thing you should keep in mind is that in India, we are going to have more and more private universities. So this has been clarified. I mean, previously there were virtually no private universities before. Everything was a public sector university. But nowadays you have private universities, and some of them are very good, like Ashoka University in Delhi or Gurgaon. Maybe you've heard of it. So Ashoka University is a very good university, and there are many other universities following suit, like BITS, like BITS. Initially it was in Pilani. Now you have there are other campuses in Hyderabad, in Goa. So more and more private universities are opening up, and they need qualified professors to go then and teach there, right, and do research. So that's another exciting option. Could be an exciting option. Then of course you have a research and development of industries, right? Because industries, what do industries do? Industries take a basic research or an finished product of a research, and then they mass produce it for lots of people, right? But before you mass produce it, you have to figure out what are the optimal ways of mass producing something, right? I mean, if I know how to make an LCD screen, very much like my phone, I would not immediately know how to mass produce it, because it might take a lot of money just to get the raw ingredients. So in such cases, you need to optimize on various things, right? And that's exactly where your training in like as a PhD would be very useful to provide a good liaison with industries. You can work with industries. Many industries have research. All industries have an R&D staff, right? Research and development staff who typically understand what is the research that has been produced from a university or a research institute. They understand the research, and then they appropriately adapt it for a wider production, right? They have to modify things also for a wider production. Then there are other careers which I'm sure this is very familiar to you. Things as data scientists and engineers for companies, right? So we live in an age where information is exploding, right? So you're producing huge amounts of data. For example, you go to a supermarket to buy some stuff. The supermarket keeps on track of whatever products you're buying, and accordingly you get a promotion in your inbox that, oh, you have bought so many chocolates. If you buy another chocolate, we're going to give you 10% off. Right. So all these things that come to you, they are not coming magically, right? There is a lot of engineering behind the data. So whatever, so sometimes they're creative as well. In many cases, they're creative. So this data scientists and engineering this is an integral position for many companies. They need to understand their consumer base, who and what. I mean, how many people are consuming what. And accordingly, they will make newest suggestions, right, to maximize profit, for example, or to minimize wastage. That's also very important. So all these things are very crucial. Now, this is something you may not have imagined, but it's highly possible. I've seen quite a few of my colleagues go into investment banking. So if you understand mathematical models very well, you can go and work with banks. Because a lot of, a lot of movements in the market has to do with understanding of mathematical models. So even if you study things like economics or commerce, there are various models that people build in order to understand how commodities or how objects interact with each other. And typically, as a graduate from physics, you have a very good mathematical skill, or you should do a PhD in mathematics as well. You have a very good mathematical skill which is needed to understand what data is essential and what not. So how will you treat these mathematical models, right? So this is something that the investment bankers value a lot, but one has to be very careful. There can, if you're handling models in a not a good way, you can cause economic meltdowns. So one has to be very careful when doing this. So there's a lot of risk assessment that goes on in many of these companies. And this option perhaps was not there for us when we were studying physics, but these days is certainly at least a possibility. is that you can create a startup, and the startup can get some help from the government in order to find technologies that help the society. Just as an example that I told you, you can try and produce. There was a company which was trying to produce machines or devices which would take water from humid air and produce potable drinking water, and that too, make the humidity less and make us feel better, right? Or you can become Angela Merkel. I'm sure you know who Angela Merkel is, right? No? She was the Chancellor of Germany for around 16 years. And she was a very stable leader who went into politics, but she had a PhD in physics. So yeah, she was leading Germany for 15 years. So you can actually, and then remember, once you have your education in physics and you choose a career in politics, you might have the right vision that is needed to bring the scientific temper a lot. Good. So finally, I think I'm kind of closing my time. So what are the sectors that you could work in, right? So we've talked about the various things. You could work in astronomy and space. I think that was pretty obvious. You can work in climate science and meteorology, because climate science also needs an appreciation of various complicated mathematical models, and as well as geography and geology. Right? So again, these are topics which are highly interdisciplinary. We cannot survive in our islands alone. So the mathematical expertise you get from processing models in physics can be of use when you want to understand climate science. Education is, is of course a self-evident sector. Engineering, you can work in lasers and photonics. Lasers and photonics are very crucial to make modern day equipment. Yes. So there you see, this is one example, right? Then you have medical physics and digital healthcare, because artificial intelligence is being used, machine learning is being used more and more to kind of preempt the diagnosis. So many things like Alzheimer's or early stages of cancer, they are not always clear to doctors, right? So on the other hand, what machine learning does is that it takes the data from a huge number of patients, see what their symptoms were, and actually predict, like you can do a checkup and then they say that hopefully, fingers crossed, nothing happens, but if something happens, you should go and check a doctor. And if so, because you are detecting something early on in the onset of the disease, there are much more chances for recovery, fast recovery, right? So this is how things are important. Renewable energies, I've already also discussed. Robotics and artificial intelligence, again. You can also do gaming, right? Gaming and various kind of graphics is very important. Finance and economics is also very important. I've also just talked about it. There are sometimes many scholarships also available to finance your careers, and you can read it about here. Maybe I'll give you the slides, and maybe this can be made accessible to the students as well. Right. So I think it's time I should stop. And so my own field has been, as I said, in theoretical physics, with something to do with strongly interacting systems, which cannot be understood by traditional means. And a lot of my own work involves finding new ways to understand, strongly interacting systems that cannot be understood with traditional methods or traditional computers, for which you need quantum computers. I also talked briefly about it. I'm a faculty at some institute, so this job does involve some administration, teaching, and mentoring students, so on. If you have questions about what I do, you can.
We expect questions from.
Yes.
It's very important. Otherwise, how can it help you? That's very, very
Engineering can one do research.
Please feel free.
Yeah. Yes.
Engineering can one do research.
Oh yes. So the question, one of the question was, after engineering, can you do research? Yes, you can do that. Definitely, you can do that. Even if you complete a PhD in engineering, that is research. You are researching a new way or a new structures in something. Yes, you can do it.
Like in physics, research in physics.
Research in physics may be a bit more difficult because you see, the thing is, engineering is very specialized. If you're doing mechanical engineering, for example, you're learning more about the structures of that is also physics to some extent, but it's a certain branch of physics. But there are people who have studied engineering then do some courses in physics and do research in physics. It's definitely possible.
Sir,
It's viable, but the viable it depends a bit on what topic on engineering you've studied. So if you have studied, for example, civil engineering, right, how things work, yeah, it's not that it's that much difference, but if you want to do change and do things in particle physics, for example, you would need to have a background, you need to take some few courses to improve your background before you do physics. So some amount of taking, before you change fields, you need to get abreast with what is happening in the field. That part is essential. It's viable. It's definitely viable. You just have to figure, like you have to talk to people who are working in that area of physics that you are interested in, and then figure out what is the optimal route for you. Yeah, there was a question there.
sir, it is often said that research is quote-unquote risky. So what is the risk factor in research, and what would you rate it on a scale of 1 to 10?
Yeah. The rating part is difficult because the second part is that I've only done research, so it is risky. It is risky. It is risky on several grounds, right? One of the grounds, and I think sometimes this is a bit important, is that if you are doing research, as I said, it's a long haul thing, right? It can happen that as you are pursuing research, you will see people around you getting jobs and settling down. It's not that people don't settle down in research; they do. This always happens, but it's much more. It's much more risky, as you said. You have to take bold decisions, right? You have to say that, well, I want to do this, and let me do this. But if you decide that you want to do this, there is typically always a way that works out. So all I'm trying to say is that in research, you learn to take decisions on a much early stage, right? It's not that you have to take decisions because the decisions are risky. You have to think that you have to calculate a bit. Well, if I do this, I do this. If I do this, so you have to think about several, like at least 1 or 2 backup plans as well. And then, I mean, the more you think, the more you assess the situations at an earlier age, the better prepared you are, I would say.
Thank you, sir.
Sure. It is, as I said, it's risky, but if you have a backup option planned, then it's definitely much better.
But I would like to tell you, Debasish, you need to tell them what hard work and effort you have given for. Please listen to this part.
So one of the
It's not very easy, that also.
So one of the things that, of course, ma'am emphasized, and this is very much true, is that a lot of it is, like a lot of success you get depends on the passion and the hard work you put in. So if you are not putting in enough passion, if you're not putting in hard work, your success will also be limited, right? So this is very important. It doesn't mean that, you have to stop enjoying life and only do physics and so on. But I mean, if you enjoy research, if you enjoy doing something, the joy in doing it compensates for the hard work. The joy of achieving a result, the joy of having understood something which no one else knows at the point when you have understood it, is very difficult to convey, because you know that you are the one who knows it. You are the one who understands it, right? This is a really unique joy. And it really compensates for all the hard work that you do. You might end up, and this happened to me, I've spent up like nights maybe trying to figure out a problem, but finally when the problem is solved, and I know that it can solve it, it's really an immeasurable amount of satisfaction that you get out of it.
How many hours of work or so much input without any output at the end? It can happen.
This can happen, but there's nothing to, there's nothing to...
Not 1 or 2 hours.
Exactly, it's not 1 or 2. But also think that this is happening to a lot of other people who are also doing research. It's not that, like Einstein just came up with itself. He had like lots of years in which nothing came out. His last theories also have not proven, right? It's not that everything you do has to be successful. That's completely fine. It's the effort that counts, right? I mean, we cannot expect that you do everything and you're successful in everything. There is, very few examples of that. There's a question there.
Sir, I want to speak in continuation of what he said. Last night I was having a conversation similar to this with my mother. I told her that I look up to Sudha Murthy a lot and I want to become computer. I want to study computer science, and then I also want to, start. I love her literature, and I used to be obsessed with many authors, but these days, the culture of reading has vanished. So, and going with
Yeah.
the trend, I also don't read anymore. So, my point being that my mother told me, and this is very true, that first we especially Bengalis, they try to create a, they try to establish themselves first. I have to earn my bread and butter first, and as he said, this is very risky. So and by the time I am well established and I have enough monetary and enough resources to start my research, I feel like I am already established. Why should I even do this? So what should be, so what should, according to you, be the motivation to continue?
Okay, good. Yeah, yeah, good. So let me try to answer this in an honest and way. So what you said, all the factors that you said, right, are very much true, right? It is risky. So there are two aspects to it. First of all, there was a slide where I showed you there are some scholarships available, right? So financial, monetary wise, once you cross these hurdles, right, you can, so first of all, there are scholarships for you to help along the way, first of all. That gives a support. Second of all, once you get established in a career, right, you get into one of these professions that I showed you, the monetary compensation is not bad. It may not, allow you to fly business class all the time, but it's good. That's the first thing. So at the end of the road, what is waiting for you is not bad. I want to emphasize this. I mean, in many universities, as the quality of life, like in India, I have witnessed this 2 decades, as I'm sure many of our teachers as well. In the decades between 1990 and 2020, our quality of life has improved and it's improving, and the financial compensations and the salaries you get are also improving with time, provided you get into a good place. It is risky, but it's not impossible. That's what I want to emphasize. And the second thing that you said, it's very crucial. Is like, as you said, I'm reading, but if I give away my practice of reading to focus on something, I've not been reading for like, maybe, I stopped reading for 10 years, and then it's very difficult for me to pick up the habit after all. So my suggestion is that don't give up on the habit completely. So there have been phases I also love reading. There are phases in my life where I've read extensively. So after I finished my PhD, there was like one whole month where I read the 7 books of G.R.R. Martin, Game of Thrones, 7,000 pages. I was not doing anything else. I was in a, I'd finished my PhD and I was really not in the mood to do anything. So it was just 3-4 weeks where I read 7,000 pages. So whatever these 5 books at that time. So you should not, and there have been phases in my life where I stopped reading. So don't give up the habit altogether, whatever it is. It can be reading, it can be solving puzzles, it can be coding, whatever you want, right? There have been some things in my life which I could do better, and now I've not done it for 15, 20 years, and now I cannot do it anymore, and I regret that. So if you're really passionate about some aspect, while you are learning your things for bread and butter, don't give it up. Find some time for yourself to keep doing that habit. So those things that you find pleasure in, right, will keep your motivation and your boost levels high. Because if it's only the single goal of achieving something, it can lead to, we talk about mental health these days, right? This is a very important component. If you're really focused with something, with one aim, that's very good. But there should also be spaces where you can take yourself out from it, remove yourself from it, and get to de-stress in a way that you like. Right? So that's important. Does that answer your question?
One more question from me.
Yeah.
Like in these days, we all focus on exams like JEE and advanced.
Yeah.
After that, we get into IITs or IAS.
Yes.
What should one do after pursuing a course like CS? Can one
is in computer science or yeah. So computer science. Okay. So first of all, the way the system is set up, you have to pass an IIT or you have to pass a JEE or you have to pass an entrance test to get into something good, right? There is very little that you can change about it. This is not up to you. But what is very important and what is something that I have seen in interviewing students is that some students get very good ranks in IITs or like JEST, like there's some other exams, JEST. However, when you ask the students some basic questions, they're unable to answer that. So I think it's very crucial that you get a good rank. That's true. On one hand. On the other hand, it's also important that when you prepare for exams like IITs or JEST or something like that, you understand the subject better. Right? You have to understand, these are sometimes orthogonal things. Sometimes doing very good in exams doesn't always mean that you understand the subject better. Maybe you know the formulas, you are very fast in putting some formula to work and getting the answer out. But that doesn't always mean you understand the topic. So what my suggestion is that, you see, in life, as in everything else, you have to achieve a balance. You can say that, so you have to be good, but at the same time you have to make sure you understand what you're doing. At least to a good extent, that if someone asks you a related question, a slightly deeper question, you can answer that. So this completes your first hurdle. You get into an IIT, you get into an IISc, right? Once you are there, you have a new world for you. You have an option of, you said you were interested in computer science, right? You study computer science, and computer science is a field from where you can go to various directions. You know how to code, you know how to handle data, you know how to create applications, right? And this will let you, either you are interested in, for example, building companies, building databases, and you can get in touch with companies. It can also happen you're interested in scientific research. You're interested in quantum computing, for example. Then, side by side, if you are at an IIT or an IISc, you should make sure that you can also take courses in basic physics, basic mathematics. This will strengthen the base that you need to do research in related fields. Because computer science is a very interdisciplinary topic, right? It gives you the necessary technical skill to attack essentially many things. You can improve software that is essential for biomedical engineering, for example, nuclear physics, this gravitational wave that I showed you. So it has really a vast array of potential applications. You have to figure out for yourself what application interests you the most. So it is really a question of you yourself as an individual should understand and appreciate what is it that you want to do. Right? And then, of course, you do computer science, but together with that, you take courses, because in IISc you will definitely have options for it, to take courses in related topics that can, support your interest, make it better, and does that answer your question? IITs also have related courses, that is true. I'm not extremely sure about IIT. Yes, I think if you're an IIT undergrad, you have to take courses in physics. But what I hear from many of my friends who are professors in IITs or faculties in IITs is that a lot of engineering students do not take these courses seriously. They just do these courses because they have to get the credit to pass. This is very common. If you want to use this as a springboard to your next career, you should not do that. You should take those courses seriously. That's the point.
Any other questions? Class 12. So then we are going to end the session. Once again, how should I, it's not just thanking you, it's our gratitude, the way you are here and you have given us time, and that's for such an enriching and wonderful session. And for class 11 and 12, you have great opportunities and challenges in life. Hope what we learned today, it's a learning session for me that will help. In future, we are going to have some more sessions with Debasish, if it is possible. We will be arranging some, this in Shah Institute, we are trying that, to visit the lab And you talk about that science day, that is the end part. You talk about that?
Yeah, so in the end of February, 28th or 28th, I think, there's a National Science Day, which means that all institutes which are funded by the central government, all the institutes that I showed you, they typically organize certain outreach programs. This means that they invite certain schools to visit the institutes, and actually and visiting the institutes at that time is actually very optimal and good, because the entire institute, because they know that such a thing is happening on a nationwide scale, they really put an effort, an all-around effort, because you see, as laboratories, if they want to organize something for you, they've also to set up things. And because they know this is a common time, they organize various laboratories, various various small talks, quizzes, and so on, to motivate students or students to study science. So yeah, if you're interested, for example, we can try to do something.
We'll do that, sure. I think
sure.
they are interested. Class 12, I have promised, because last year they were not able to go. At least we will visit the lab. Also, class 11, we will try to take them in the month of February. Of course,
Sure.
with Debasish.
Sure.
Otherwise, we don't have entry over there.
No, I'll try my best.
No,
for
it's
sure.
very. You tell the security there.
Yeah. No, I will organize.
We have
it.
no variable accelerator that next to yours.
That is beyond me.
That is beyond you. Anyway, thank you once again. Have this too.